Hey data junkies, welcome back. Now, we've already had 3 videos that came before with the foundations in mathematics, solving a one-way ANOVA by hand, and just recently we started talking about the different assumptions you need to know about doing a one-way ANOVA. In this particular video, we're going to go back to where we did the version by hand. We're going to revisit the Munchkin and the Wicked Witches example, and we're going to recreate it in R and show you how this works. So let's go ahead and get started. So the first thing I need to do is I'm going to start entering the data into R. I don't have it as a separate file, so I'm going to be entering it in manually. And so I start with a data frame. I pipe in 2 particular variables into that data frame, one called complaints, one called region. And complaints, those are just the numbers that are being brought in the particular order. And then with region, I'm also using a rep function to help repeat the different regions so I don't have to type so much. Once I have those in place, let's go ahead and start with some of the assumption checks. These are some of the pre-tests. The independent data. I'm going to trust the Wizard of Oz that he did a good job selecting his munchkins. They were chosen randomly and with equal probability, and so we're going to have good, true, independent data we're working out here. The next one is dealing with the numeric DV, and it doesn't have outliers. That was the number of complaints of Wicked Witch activity. That is a numeric measure, and I just put it into a box plot here. Now I'm looking at the tail and the whiskers. I don't see any outliers up above and down below, so I'm pretty good there. 2 thumbs up so far. Then I said, all right, do we have equal sample sizes? Now I'm plugging in the region variable into a table, and I'm looking at the counts, and I see that I have 5 munchkins in each of the 4 regions. So I do have equal sample sizes. Thumbs up. All right, the next one, we're going to get a little more the trickiness here. We're looking at the homogeneity of variation. Homogeneity of variance. Homogeneity of variance. And so this one I said you can start with a quick eyeball check. I'm doing a box plot. And I'm just doing a box plot on complaints tilde by the region. And that's going to generate for me 4 different box plots out here. You're going to see immediately that some of them are higher and lower than others. In the previous video I said, don't worry about that. What you need to pay attention to is the size of the box and the length of the whiskers. And for the most part, although the median markers do seem to be differing between the different boxes, the lengths of the boxes themselves are fairly similar to each other, and the lengths, for the most part, are okay. The south looks like it has, some longer whiskers going on, a little bit closer to the east, but then the other's a little shorter, so maybe the boxes were okay, but the whiskers are a little iffy. So let's go into our Levine's test and see what it says. So now I bring up Levine. Remember, this is in the car library. So I'm doing the Levine test, complaints tilde on region inside, center equals mean. That's comma, center equals mean. We have a smaller sample size group here, so it would be a little more tough to get away with doing the median here. But it generates out and says that the Levine's test for homogeneity variance using the mean is that my p-value is 0.9184. Well, my alpha was 0.05 previously, so this p-value is far above 0.05, so thumbs up. I have variances that are, I don't have to worry about unequal variance. I have equal variances. I failed to reject the null of the variance test that says I do have equal variances. Great. So, once I have all that, I've checked all my pre-test checks. How can I enter the ANOVA into R? Well, we use an AOV function to start off with. AOV. And inside the AOV, I put, just like I did with the Levine's test, my DV tilde my IV. So in this case, I do AOV on the complaints, tilde, the region. All of these are inside the Oz data set. And that's going to go ahead and give me the outputs for the sums of squares and the degrees of freedom. That's nice. It doesn't really give me much more I need from there. I want an F ratio. But what I can do is I can take these values here and I can calculate the F ratio. When we did this by hand, we were generating up the sums of squares and the total sums of squares and all that good stuff, and it generated us to the MSB and MSW. Well, I can get those from here. Note, I have the degrees of freedom within and between, and I have them for the sums of squares. Now, where it says Oz $region, that's my between. That's the variation between the group metrics, the sums of squares between, the degrees of freedom between. The residuals is synonymous with within, or error. the stuff that we don't know. So I have the sums of squares within is 19.2 and the degrees of freedom within is 16. So once I have those, I can go ahead and just do a little bit of math and later, and I'll figure that out. But for now, I want to go ahead and I'm going to save my AOV as an object. All right. I'm going to come back to do the F test stuff in a minute later, but I'm going to do one of my other assumption checks first here. So I'm going to save my AOV as an object. I'm calling it AOV.whiches. And then I can plug that AOV.whiches into a summary, and lo and behold, this is the magic right here. This is what I call an ANOVA table. And the ANOVA table, on the farthest most left, it tells me the independent variable I'm using of region, residuals underneath. Across from that, I have my degrees of freedom, then my sums of squares. Those came out from the AOV function before, but here they're being plugged in, and it's doing the extra math with us that we could use to generate the F statistic. Because across from that is the mean sums of squares, the mean squares, and then next to that, the F value, next to that, a P value of the F statistic. So in this case, we don't need an F critical value. We have a P value for the F statistic. Fantastic. And again, how we got this done is I saved the AOV as an object and I plugged that into the summary. Instead of saving the AOV as an object, you could just put the entire AOV function inside, nest it inside the summary, and you'll get the same results. Note at the bottom of the summary function here, I have these what I call cheater codes, where I have a number of stars, and the number of stars are indicators that tell me how statistically significant am I. And the p-value up there is 0.000466, which is very small. And notice that it's 3 stars. The 3 stars corresponds with 0.001, so I'm statistically significant at an alpha of at least 0.001. And it could be smaller, but I don't have any smaller on this sheet here. But if I'm significant at 3 stars, I'm also significant at 2, at 1, and so on. So, moving right along then, I also just want to point out here that because I have the summary table here with all of the pieces, if I was ever given a situation where I was missing some of the pieces, I could calculate my way through to get to the F statistic. Just like I said before, if you just had the AOV and it gave you the degrees of freedom and the sums of squares, you could divide the degrees of freedom into sums of squares to give you the mean squares. Divide the mean squares gives you the F statistic. And so this slide here tells you how you do that division process to get towards F. Now, as an alternate form, we have another function that can give us an ANOVA. How fantastic is that? A whole extra function that gives us another option. Now, and this is good for different reasons here. This test is what we call the one-way dot test. And there's different kinds of tests you can use with this function. We're using it as a one-way ANOVA for now. So the one-way dot test, inside is the same as it is for the other ANOVA, DV tilde IB, or in this case complaints tilde regions. And there's a variance option in there. The default is that the variance is equal to false for unequal variances. We're going to come back to that one soon enough. But in this case, I did have equal variances according to my Levine's test. So I'm doing an option variance equals t for true. And that gives me the one-way analysis of means. And it gives me the same F statistic, the same degrees of freedom for both within and between, and a p-value. So note here, instead, it says the degrees of freedom for numerator and denominator, so you'll have to know which ones are the betweens and within when you're pulling these out. And the p-value is associated with the F statistic. How fantastic is that? And when I have that, I can just go ahead and use that information. But what I'm also going to do here to show you some differences between these two tests is I'm going to store this one-way dot test as AOV.whiches 2. So I have AOV whiches and AOV whiches 2. And I can compare these. I'm going to do an attributes command on both of them side by side and show you that they have different stuff in between. When R does the calculations, it gives you the F statistic and it gives you some information. But the machine that moves in the background of R saves other information related to the test. And depending which function you use, you get different information. The one that has the AOV whiches, that use the AOV function, that one has an option in there called residuals. And that one we're going to need to do our assumptions test. The other one, the one-way dot test, is very useful, as you're going to find out when we come to the Welsh version, but it does not give us the residuals. So depending on what happens with your analysis, you may need to use both functions as you go through this. So once I have those residuals and I had it saved as an object, and you can only get access to those residuals if you save it as the ANOVA as an object. If you just try and do it with ANOVA out of AOV and put a $ after that, doesn't work out. So when you're checking with your normality, we're going to create a QQ plot. And in this QQ plot, I start QQ plot, open parenthesis, put in my AOV.whiches, which is the first one from the AOV function, $residuals, treat it just like a data frame where it has columns of information. So here I'm using the residuals, and then I put in some extra plot flavor text. You can close it after the residuals. You don't need anything else. But in order to make it look a little nicer and appear up on the slide here for you, I did some other things like change the dots, change the size of things so it appear when I put it into the slide for you, things like that. But then what's more important is I follow up with a QQ line function. QQ line on that same residuals, AOV.whiches, $residuals, that's all you need from there. I put in some extra stuff. But once you plot that in, it will plot the line to see that the data points should be hugging or not. And in this particular QQ plot, it's doing a really good job of tracking that particular line. So we have no issues with normality here. So this happens to cover all of our particular tests that we need to do to order cover this in R. We checked the different assumptions, and through the one-way.test and the AOV functions, you can have two different approaches on how you can go ahead and get your F-test results in R. And I'll see you all in the next video.